Welcome to the Excite training module on writing Python programs, standalone programs for scientific computing. This will extend what we started in the Linux command line module previously, and will also refer to some things that we should remember from the PE100 series courses, modules on Python programming for Jupyter. And in fact, speaking of Jupyter, um, what's the fundamental difference between writing Python for Jupyter or writing Python for standalone programs, right? Both are perfectly valid, perfectly useful things to do, and both have their place. When you're writing for Jupyter, you tend to be doing interactive exploration, poking around with the data, trying a few things, see what works here, sort of start to refine your algorithm a little bit, figure out what you're doing. When you're writing a standalone Python program, you're typically going to be writing a piece of software that you intend to keep using over and over for some period of time. It's not an ephemeral transient artifact like a Jupyter notebook. Sure, you can save a Jupyter notebook, but it's not intended for um, general purpose computing. Whereas a Python program can actually do anything you can do with a computer. You can do with a complicated enough Python program. You could write interactive 3D video games. They might not be great. There are better languages for doing it, but you could do it. That's sort of the point there. Relevant to us, when you write a Python program, it's a lot easier to take advantage of parallel or distributed computing environments, such as the Linux cluster operated for chess. It is not impossible, but more work than it needs to be. More work than it needs to be to try to do this in Jupyter. Whereas with a standalone Python program, it's fairly easy. You can either write your own explicit support for parallelism, or you can use one of the distributed computing managers like Pegasus that you'll see in the workshop this year. Um, the other thing that's very useful about writing Python programs is that they can act like Linux commands. You can, in essence, extend your command environment by writing programs that do common things. We've seen programs like head and tail to look at the first few or the last few lines. You could write a Python program that picks, for example, goes to the seventh line of output because it's a file off of some interesting instrument, goes to the seventh line, looks for the first three numbers and averages them. Okay, you could write a program to do that, and you could call it, daily, and save it in your bin directory and just type daily. Daily becomes a new Unix command as far as you're concerned, and it does this quick check of your instrument output every morning for you. Okay, so you can extend your environment that way. It's a very, very powerful kind of tool. Um, let's take a look at some actual Python programming. Here we go. I created a directory and put some files in it, some handy files, examples. I'm going to show you a little command line trick. So I typed enough characters to be unique, actually a little bit more. I got type PY and a capital E because it's a case sensitive. I'm just going to hit tab and it completed the rest of the file name. Okay, very handy thing. I'm not a great typist, and so I rely on this all the time. Handy little thing. So we have in here. I've got some sample data for us to work with. This is actually from the XS 100 modules, X-ray science. This will extend their example in a few moments. So let's take a look. I'm going to make a very simple Python program. I'm going to create one called trivial.py. Very simplest couple of print statements. Save it. Exit out of here. Now, I can, to run this, type Python 3, the Python runtime environment, Python version 3, and I recommend you always use version 3, at least until 4 comes out, if it ever does. Python 2 is on here for historical compatibility purposes, but it's not maintained really anymore. And it really is obsolete. Use Python 3. Okay, so Python 3, hey, and it runs it. Okay, so this is, yeah, it works. It's not exactly going to be a single command. I couldn't just, if I try to just run it like that, you know, it doesn't even know where to find it. If I say, okay, current directory slash trivial.py, so it doesn't even have permissions. I could give it execute permissions, but even then it would fail, because what would happen, it would look at this with no other indication and think, oh, well, it must be a shell script. And we talked about shell scripts at the end of the Linux commands. Thing is, this isn't valid bash commands, right? We could use echo, but we can't, you know, there's no print function that we can work with. So we need to tell the OS, oh, hey, this trivial.py, it contains statements that we want to be interpreted by the Python interpreter. So how do we do that? I'm going to add a line at the beginning with a pound sign and an exclamation point. All scripts will begin with that. Type. Okay, so what we've got, we're saying with the pound sign exclamation point, this is a script. I want it to be interpreted by something that knows how to read scripts. And the rest of the line is what I want to use to do the interpreting. Okay, so I want the Python 3 interpreter to interpret the rest of this file. Right? Okay. I need to do one more thing. What did I need to do? Let's take a look here. None of these have an X in them. The execute permission is not available to anybody. So like we did last time, I want to add permission to execute the file to everybody. Okay, so what we have now. We've got X's here indicating that it's executable, and ls, when it color codes its output, in fact, give us the output. Now it's printed in this kind of light green. Kind of telling us, yeah, something different here. Check and see. Oh yeah, that's because it's executable, right? So it's color coded for us. If I now try to run it, Still says it's not found. Why could that be? How does it know where to look for an executable? Right? When we type ls, how does it know to look in user bin and run ls there? How does it know how to do that? There is a special kind of variable in the shell called an environment variable. It describes the environment in which you're working. And one of those variables is path, all capitals. So looking at echo, so I can print out its value, $, I'm looking at a variable, and then path. This is a list of the places that it's going to look for commands if I don't specify otherwise, right? So it's going to look in places like user local bin or user bin or, well, one of my favorite, /home/escot/bin. All right, so if I put my little trivial program into move it into that directory, now I can run it. All right, let's take a look right quick. So we put that command into home escot bin, or you put it into the bin directory below your home directory. Okay, so we can create our own commands. We don't have to have the .py extension. That's completely optional. Right, let's take a look here. Move. This time I'm not going to change its directory. I'm just going to change its file name inside that directory. Right, so now it's named trivial back in my home directory. I can run it from anywhere and it works. Okay. The world's kind of divided on when to use, whether you use .py on everything or not. If it's something that you're going to write basically to be a command that you're going to run a lot, then it's probably good to follow the Unix convention and leave off the file extension. If it's something that you're writing for maybe daily use, but not constant use, go on and put the .py extension on there, just so when you're looking at it at 1 o'clock in the morning when you're tired and you just want to go somewhere else, and you look at it and see .py, you instantly know, okay, that's the Python program that I had in there. That's not my data file or anything like that. So yeah, it can be handy to know. Let's see. A few more differences between Jupyter and a standalone program. Jupyter has a library of little widgets that you can embed in a Jupyter notebook. You've got sliders that'll change a value and assign it to a variable. You can have push buttons and check boxes for different configuration things. Um, it works completely differently in standalone Python programs, and it's a little bit of work. Writing GUI programs in Python might not always be the best fit. You can do it, but generally speaking, these are going to be strictly command line tools. You're going to run it in a console window. I'm using SSH here. You're going to run it in a console window, prompt for text input, print output as you go, manipulate files as needed. So it's you lose some of the Jupyter widgets. Plotting is a little bit more work, and it can have some advantages that it can plot and save the output in a file. So if you're putting publications together, you can get gorgeous output saved to a file, but it is more work. So, that's the trade-off there. And then fundamentally, the big difference between writing code for Jupyter and writing standalone programs is with Jupyter, the flow of control through the code is to a larger extent dictated by the user. As you run each block, you can decide, okay, what's the next block of code that I should run? Is this relevant to what I'm doing? No, I'll skip it. Whereas with a standalone program, you've got to use if statements, case statements. You have to be very explicit about your flow of control. When you're writing standalone Python programs, your software development kind of reflects a more engineered approach, a little less of a exploratory kind of way of going about work. All right, I want to walk through an example, maybe a couple of examples, and see just a little bit more of how these standalone programs are created. Some of this is going to look a little bit familiar from Jupyter, but you'll see a little bit different application of it. So in this examples directory, I've got a couple of data files I can work with. Well, I've got 4 data files I can work with, and I went ahead and wrote out a demonstration program, so you don't have to watch me type. Let's take a look at. We'll kind of interactively fire this up and see what we're doing here. I've got. We'll start off with this one. So let's take a look at readings.csv, comma separated values. Very, very common numeric, very common way of representing data. Arguably not a great way to do it, but very, very close to universal. So I've got a file that contains 4 lines, 3 numbers. We'll treat them in different ways. And what I want to do is take averages of each column. So let's look at how this works. Very first line. Okay, I'm specifying, hey, this is a script. I want to run it with Python 3. I want it to do the interpretation. You will hear people use the term Python program and Python script almost interchangeably. There might be an implication that scripts are smaller pieces of code and programs are more complicated. But there's no technical basis in that statement. The syntax for launching the Python interpreter to execute your program uses the mechanism that Unix has used for interpreting scripts since the 1970s. So when you look at it, there's a tendency to say, okay, I'm using this script interpretation mechanism, pound sign, exclamation point. So it must be a script. But this is a full-blown program. Either term is fine. All right, so what I'm going to do in this program, we'll kind of step through the code here a little bit and see. I've got some totals of my 3 columns, and I have a variable called records that keeps track of how many records I've read from that file, how many lines I've read from that file. Notice a couple interesting things about these numbers. FM total, AM total, they're floating point numbers. They're initialized to 0.0. So they will keep fractional components. TV total and records, they are integers, right? No fractional values. They can only hold whole numbers. I want to open readings.csv, and this R in the second argument indicates I want to open it for reading, just to be really explicit. If I don't specify anything in that second position, well, it opens for reading. But here I'm being really explicit. If I would need to change it later, and it's sitting there looking at me, I know exactly where to change. So with opening that file as results, in other words, we're going to open that file, and the file descriptor that I'm going to read from is going to be called results. With that, I'll read in a string raw line from that file descriptor using the readline method. We've seen this before, and we did this with the Jupyter examples. And now I'm going to say while that raw line is not equal to the empty string. In other words, while I'm still able to read more and more lines. Okay, I'm going to print out just for my own handy knowledge, I'm going to print out the raw line read from the file and show what line was read. I'm going to then call the method split on that string. And what that does, it's going to run a function that will take that string and return a list of values where each value is however much of that string went up to the next comma. Okay, so we're going to take that line, break it up at the commas, and each part of that is going to become a value in a list. Then we'll print out what we saw. Okay. Then, now that I've split it up into a list, I can read those parts out of it. I can tell what the FM, AM, and TV values are by looking at the 0th, first, and second elements of that list. Okay, so the first element is the 0th, the second element is the first. Oops, I don't want to do that. Sorry. Okay, I'm not sure what I did. Then the third element is the second array, right? This counts from 0. Kind of thing only a computer scientist could love. All right, so I've got those values. What I've got here is these will be string values. And we'll go through this. And then finally, I will convert those strings. I'm going to convert them into the first two into floating points, floating point numbers, and the third one into an integer. Save them in AM frequency, FM frequency, and channel. I'm going to increment records. Right, I started at 0. I've read the first record now, so I can increment it. I know it's in there. I'm using a syntax that I think we very briefly discussed in the Jupyter section. I've got it here just to emphasize that it exists, and so you'll see it again. FM total plus equals FM frequency. In other words, it's saying FM total equals FM total plus FM frequency. Okay, it's a shorthand notation, but you'll see it fairly commonly. So I've got these 3 running totals that I'm keeping, and then I go ahead and read the next line. Very common idiom here for reading from an input file until you know you've read everything. You'll see this structure. When it's done with that, it'll loop back up to the top here while raw line not equal to the empty string, and goes through it again, right? That while is going to run until you run out of lines to read. Finally, compute the averages, and it'll print the averages. All right, so let's see this running. I'm using, in this case, I don't want to have to put it in my bin directory, so I'm using // Let's start at the local directory and execute. It's not letting me. And we know why, because it's not marked as an executable. Okay, so it read this raw line out of the file, read that as a string, and printed it out. Then it split it up and broke it up into the 3 parts separated by commas on this line. So the first string was 106.5, the second string of characters was 680, third string was 12. Here we can tell it's printing them out as their here we can tell their value as strings as it's printing them because we see these quotation marks. It's telling us, yeah, this isn't a number, this is a string. That's why we had to explicitly use float and int to convert them to values that we could do math on. Okay, so we keep our running totals as we go through, we count how many records there are, and then we print out our averages when we're done. All right. Fairly simple kind of example, but it shows a few things that we're interested in. Right. So something I don't know if we've seen before, the with statement. With is handy. It will catch an awful lot of errors and give us a single place to deal with errors if it can't open a file. It will close the file automatically when all this code is done running, when that with block goes out of scope. In other words, when it's done, it'll close the file. We don't even have to clean up after ourselves. So that's a very useful way of working with files, of opening them. We've seen now a while statement checking a condition to see if we've read everything in a file. This is a very common thing to see in Python code. I just about guarantee you will write something like this before you're done because you'll need to step through an entire input file and work with it. We talked about in the Jupyter modules, we talked about split, but here it is emphasized again. A common thing to do because you'll see a lot of CSV files and scientific data, business, the whole universe, pretty well standard, even if it does make things a little complicated. And one more idea that's useful is seeing, okay, so as we need to debug this thing, one way of doing it is putting in a bunch of print statements and run the program to a point where it has trouble and see what had been printed out, and you can see the values change. Okay, there are other tools for debugging Python. Choose, whichever ones you like. I like Spider simply because it comes with Python and it's installed everywhere, and I don't have to worry about whether it's there or not. There are various IDEs that integrated development environments that people use, and that'll work pretty much the same way. So, pick one. Spider works well over SSH connections. Most of the others don't. Let's take a look at just very quickly another format for data. It's superior to CSV, and I think it's increasingly being used, and I look forward to a day when it's more or less universal. This is JSON, the JavaScript object notation. It was so successful, it isn't just used for JavaScript anymore. Most languages support it one way or another. This JSON file has three elements in it. The first one is a number named int. The second element in here is named array, and it is a list. You can see it inside square brackets. And the third and final element is a dictionary named creatively dictionary. And it contains keys and values. And we'll take a look at what that means here in a second. So this is a structured file that is somewhat self-describing. We can look at it and tell what the structure is. We can look and say, okay, this is definitely a standalone scalar value. This array, this list, this is definitely a vector of 3 numbers. Okay. Dictionary is going to have strings associated with it. Now, if this was a CSV file, we would see 1, 1, 2, 3, sum comma 0. Um, and we wouldn't really know what the structure was, right? There wouldn't be anything obvious if you were looking at that in a CSV file. Um, you wouldn't necessarily know that that first value was a scalar. This could be two lists. It could be a 3-element list and a scalar. You wouldn't have any way of knowing. But here we have at least a glimmer of what the structure is. We might not know what it means. We might not know if these are counts or kilograms, but we at least have an idea of what the structure is. All right, so let's explore a little bit. I'm going to run Python 3 interactively. Instead of typing a program, I'm just going to enter Python commands and run them here. I want to open and process the contents of that JSON file. I can either write a lot of code to open that file, read it line by line, parse it, split and trim and all kinds of things. Or fortunately, somebody has already done all the work for me. So I can just say import JSON, and there you go. I've got code that is in fact supplied with Python, written by somebody else that understands how to parse and manipulate JSON. Let me go ahead and read that data in. I'm going to load the results of opening file.json. Yeah. Okay. So I'm going to use the JSON load method. Load takes a file descriptor. The file descriptor is going to come from calling open, and I tell open, hey, open file.json. Then I have these two closing parentheses, close the first one, close the second one. Okay, just like function composition when you took calculus in high school, remember? Same kind of concept. All right, it just opened that file and read all that data. Let's see what it looks like. Lo and behold, it read that in, created a dictionary of values. We can tell by the curly bracket there. The first one of which, the first element of that one is a field called int, has a single number in it. A field called array, and it's got that vector of 3 numbers. And then finally, we have a field called dictionary that stores some keys and some values. At that point, we can make some manipulations here. So we could say data. Let's see if I can do that. I was able to set the value of this field int, set it to 4, and it's reflected here. I can so print the element number 101 of array. That's that value right there. I can manipulate the dictionary. Okay. So I have now added to the dictionary with its columns named key and value. I added a key sum and I set its value to 6.5. All right, so we can manipulate the JSON object, and then when we're ready to, I can print out. Um, that's useful file descriptors. All right, never mind. And then I can print out the value of it. I could save it to a file. This gives me tremendously more flexibility than um, trying to deal with CSV files or some kind of homegrown file format that I've put together out of the blue. Whole lot of work. JSON will it's a reasonably good and general purpose way of representing data. There are file formats that are commonly used in that are discipline specific in some cases. In geosciences, you'll see HDF5 used a lot. It is designed to make life easier for people that have to deal with things that occur at coordinates, for instance. Um, and fortunately, there are not Java, there are Python libraries that you can just import and it knows how to deal with it. Right. So a lot of these specific file formats for very specific problems. A lot of them have support in Python. So when I started this example, one thing I did was I imported uh, a module. I said import JSON, and it told the interpreter find a module, find a module by this name, and as an interpreter, I want you to start being aware that module is here and it's got functions and constants and stuff in it that are useful. Start using that, right? So all my JSON commands, when I first fire up Python, it doesn't know how to deal with JSON, okay? All the ability to deal with that comes from importing that module. All right, so what if you need to import a module of some strange module. Well, I don't know, maybe you need HDF5 support. The operators of the Linux cluster, they're not going to let you import your own modules for use by everybody. Um, they might do it for you if they know it's going to be completely safe, but generally speaking, they don't want to start adding a whole bunch of stuff system wide for security reasons and just for managing purposes of managing complexity. Um, the complexity can come from multiple versions of things. And you can get in a situation where somebody needs, I mean, this is very common, where somebody needs version 2 of something, somebody else needs version 3. And how do they specify what they need? Are they compatible with each other? Usually, but sometimes not. So it's good to have some isolation. It's good to be able to install something in your local environment, not system wide, so that you can control exactly what versions of things you're dealing with. And we do that. There are different ways of doing that. The Python virtual environment, um, that infrastructure, that framework is very commonly used. Let's set one up. Python 3-M, I'm going to run the module VM for virtual environment. I'm going to create an environment called my_enviro. Let's do that. So it is building this virtual environment. It's going to take it a moment. And it's completed successfully. It created a directory called my_enviro. And inside there is um, um, enough information to basically have my own private Python installation and whatever modules I need. Now, just because it's there doesn't mean I'm using it yet. Okay, that VM command, it set up the environment, but it doesn't start me using it. For that, I need to enforce what's in here to be executed. So the source command um, runs the shell commands in a file, myEnviro bin activate. It runs those commands exactly as though I typed them in this terminal. All right, so that's that way it can modify some of the state of the command line interpreter that I'm using right now. And part of the part of the environment of that command line interpreter is the prompt. So notice that the prompt over here changed. Okay, so inside parentheses, it's telling me, okay, good, you're using myEnviro now as your Python environment. So I can do things like pip3 is a package manager. Um, requests is used for manipulating HTTP. There we go. Okay, so it installed um, 5 packages behind the scenes, one of which is security certificates, the current version of that. Not exactly the kind of thing that system administrators want to tamper with too often. You know, what if you installed an old version? You could actually, yeah, if you did that deliberately the right way, you could actually have some fun that way. No, I didn't say that. Uh, so it's installed, I think I counted 5, yeah, 5 packages. So you got the package that you asked for and 4 of its dependencies. It automatically computed, oh, okay, if I start with this package, what dependencies does it have? And it will continue to fan that out forever. No, well, it'll check for loops, and it won't go through a loop. But if you install a package and it has dependencies, and those dependencies have dependencies of their own, it will continue to uh, traverse that tree and get everything installed. It can do multiple packages at the same time. It can, if you have quite often you'll have a package that can specify a range of versions of one of its dependencies that it can deal with. Generally speaking, solving that problem is mathematically a hard problem. It takes a lot of work to solve it in the general case. Usually it's pretty easy. Usually it's, oh, just give me the current one, and you have a pretty trivial solution. But it can be really, really complicated. And so all of these package managers make an attempt, a strong attempt to compute a workable solution. It might not be a minimal workable solution, but it'll try to compute a solution. Um, and it takes a whole lot of work away. So it's a very useful thing to be able to use. Okay, so I've installed these 5 versions, including this somewhat, suspect looking one. It's not suspect. It's just the kind of thing that, you want to be aware of. When I'm done, the command deactivate um, sets things up so that I'm not using that environment anymore, restores my prompt back to what it was. If I run Python now, it's like I had never done that install. Um, so it lets me isolate my changes from other people's changes, and it's really, really useful. All right, so that's a introduction to uh, Python programming, uh, especially as we're interested in it for scientific computing. Um, there'll be one more module where I'm going to talk about some command line things a little bit more. We're actually going to look behind the scenes at what's actually going on instead of just treating it as an abstraction. Um, and yeah, so if you have questions, problems, I'll see you first at office hours tomorrow, May 28th. Or failing that, I'll see you at chess.